Guys, we're going to go ahead and start your semester review. This is everything that you need to know for your final that you'll be taking this week. Now, to start off, we see that we have basic research, applied research, technological development. Basic definitions of these: basic research is done to increase the knowledge, applied research is done to solve a problem, and technological development is done to improve the quality of life. Technology, its basic definition is the application of knowledge for practical purposes. So what we see is basic research is done just to increase the knowledge on the subject matter. Applied research is done that we want to solve a problem, and technological development is just the application of applied research in something that improves the quality of life. Now, the types of properties that we talked about earlier in the semester, we talked about physical changes and we talked about chemical changes. Now, the physical changes basically is just the characteristics that can be observed or measured without changing the identity of the substance. And the main thing here is without changing. Guys, the main thing about anything physical changes or physical properties, we never change what the substance is. When we're looking at ice and thinking about water, if we take an ice cube and melt it, it's still the same. It's still water. It's still H2O. It's just in a different state. So that'd be like an example of physical change. Now, a chemical change, it relates to the substance's ability to undergo changes that transform it into a different substance. Basically, what we say here is that anything chemical change, chemical reaction, we see that it changes into something different. It transforms into something completely different. We cannot get it back to what it was. We can look at examples of that. We're talking about rusting or combustion, tarnishing, hardening of cement. We see that it changes into something different and we can't get it back to its original state. Now, some important SI base units that we have here. We have length, mass, time, temperature, and amount. We see there's symbols written right here. And we see that they stand for meters, kilograms, second, Kelvin, moles. And we see their abbreviations over here. Now, the one thing that we need to know about these SI base units, we can add some prefixes to them to change for the amount. To see if either a smaller amount or larger amount, but we see that we're measuring here with meters is length, kilograms is mass, seconds is in time, Kelvin is the temperature, and mole is a quantity or an amount of something. Now, the prefixes that we can add to them, we can add, usually we'll deal with mega, kilo, centi, milli, and micro. And we know that a mega is going to be 1,000,000 times larger, kilo is going to be 1,000, centi is 100 times less, milli is 1,000 times less, and micro is 1,000,000 times less. Main thing here, guys, if we're going from big to small, so we're going from kilo to centi, big to small, we're always going to end up multiplying, and going from small to big, we're always going to end up dividing. Now, volume is not an SI base unit. It is a derived unit. And we see here what we have where we get unit from is just length times width times height. And what we see is we have meter time meter time meter, which give us meter cubed. Now, in chemistry, we use centimeters cubed or milliliters because basically they're interchangeable. Because this equation down here, what it does is it tells us that 1 cubic centimeter equals 1 milliliter. And that's a biggie on your test tomorrow. Make sure you know that. 1 cubic centimeter equals 1 milliliter. Now, density is the ratio of mass to volume. The equation for density is density equals mass divided by volume. The SI unit for density is kilograms over meters cubed. We normally use grams over cubic centimeters or grams per milliliter in chemistry. Those usually we're dealing with smaller amounts. Now, an example of density, what we have here is from your study guide. It says, what is the density of an object with a mass of 25 grams and a volume of 50 milliliters. So we have a mass of 25 grams, a volume of 50 milliliters. And I think in your review it's cubic centimeters, but remember they're interchangeable. So we know that density equals mass divided by volume. So we set this up and we'll have mass on top, which is 25 grams. We'll have volume on bottom, which is 50 milliliters. We go ahead and divide those guys out and we'll get 0.5, and our unit is going to be grams per milliliter. Now, moving on to looking at Fahrenheit and Kelvin, and really the only thing here is they're both temperatures, so we're just going in between them. The equations that we need to know, we know that Kelvin is going to equal degrees Celsius, and that would be plus 273.15. And we know that Celsius is going to equal Kelvin minus 273.15. Remember, Kelvin is based off of absolute zero, so you can never ever have a negative Kelvin temperature. So looking at this one, we have 298. We would plug it into, we have a Kelvin temperature, and we want to take it basically just to Celsius, not to Fahrenheit. So we would take it, plug it on in, and we would see they have degrees. We'd use this equation because we have Celsius, or we have Kelvin, and we put whatever we have in the equation. So we'd see we'd end up with Celsius equals 298 minus 273.15, and we see that we would get right around 25 degrees Celsius. If we wanted to take that to Fahrenheit, all we'd have to do is just plug that Celsius temperature into the Fahrenheit equation. Now, using significant figures, guys, if you have a problem with significant figures, you need to go back and watch the video. It's back in chapter 2 on this. Now, calculating with significant figures, when we're adding and subtracting, we always end with the least number of decimal places. And what that means, when we're looking over here, we're looking at the least precise number. And we see that, for an example, what we'd have is we see the 2 ends in the tenths place, the 5 ends in the hundredths, and the 8th ends in the thousandth. Now, the least number of decimal places, the least precise, is going to be the 1 to the 10th place. So what we do is we round everything to the 10th place, and that 9 would round that 8 up to a 9. Another example of this we see from our study guide, and what we have is we have 275.25 plus 25, and these are both centimeters. So we would end up with 275.25. We're adding that to 25 centimeters, and we're adding that up, and we get 300.25. Now, when we're looking at this, the least decimal place we know is the ones place. If we get confused on that, guys, just draw straight lines down, and what you see is this is the line that hits all three numbers. So we would just round to that place, so that 2 does not round that 0 up. So our answer would just be 300 centimeters. Now, moving on here, we're going to move on and keep on talking about significant figures and calculations. And we're looking at multiplying and dividing. And here we need to make sure that we end with the least number of significant figures. So when we're looking at a multiplication, we see in the first number, 34.6, it has 3 significant figures. Here in 12.1, we have 3 significant figures. And then lastly, in 1.2, we have 2 significant figures. So our answer must have 2 significant figures in it, and we see that it does. In another example, we see this from our review. We have 2.07 times 10 to the 7th and 4.2 times 10 to the 9th, and we have to multiply those two things together. Now, remember, when we're plugging these in the calculator, we don't put times 10. Remember, we're going to put E in the calculators that I have in class. To get the E all by itself, you would just press second comma. And basically what it would look like in the calculator, we have 2.07 E7 and times 4.2 E to the 9th. And we see that looking at significant figures, 2.07 has 3 significant figures and 4.2 has 2 significant figures. So when we multiply these guys out, we'll get an answer of 8.69 times 10 to the 16th. And we'd round that to two significant figures. So here's our first, there's our second. So that 9 does round that 6 up to a 7. So our answer would finish and be 8.7 times 10 to the 16th. Now, moving on, we'll talk about Dalton's atomic theory, and we really need to know some of the similarities and differences in this, the main things that he did. Remember that Dalton was famous just because he was the first person to produce an atomic theory and think this way. Now, he said that all mass is made of atoms, and that atoms of the same element have the same size, mass, and properties, and that atoms cannot be subdivided, created, or destroyed, and atoms of different elements combine in whole number ratios to make compounds. And lastly, in chemical reactions, atoms are combined, separated, and rearranged. Now, he was right on a lot of things, but he was off on a few. We see that first, that atoms of the same element have the same size, mass, and properties, and we see that's not true when we look at isotopes. And we also see that that atoms cannot be subdivided, created, or destroyed, and we know that they can be subdivided into protons, neutrons, and electrons. But the reason why we learned Dalton's atomic theory is because it was the first, it was original, it was the first of its time, and it was revolutionary. Now, moving on to some other discoveries, we looked at the discovery of the electron. J.J. Thomson is accredited for the discovery of the electron, and he named the particle. Now, we also look and we see that Rutherford was credited for the discovery of the nucleus. So we see that we discovered the electron and then discovered the nucleus by shooting those alpha particles. Moving on and talking about specifically the atoms and the isotopes. Now, looking at the atoms and the isotopes, we see that isotope is basically, it is a atom that has a different mass, a mass number. So it has the same number of protons, because remember, the periodic table is arranged by the number of protons. So we know that an element is an element because of the number of protons it has. So we can't change the number of protons, but the mass changes by the number of neutrons. So we see in carbon-12 we have 6 protons and we have 6 neutrons in the nucleus. But when we move to carbon-13, we see that we have 6 protons still, because it's still carbon, but we have 7 neutrons because we've increased the mass, and in carbon-14 we have obviously 6 protons because it doesn't change, and we have 8 neutrons. And we need to know that if we can add neutrons, and that just creates a different isotope. But if we add or take away electrons, we're changing an ion. But we cannot change the number of protons without changing the element. So if we can't add protons, can only have different numbers of neutrons and electrons, meaning isotopes and ions. Now, the mole. Remember, we studied the mole, and the mole, we said that 1 mole is just a quantity, and we looked at that earlier in our SI base units. But remember that 1 mole always equals 6.022 times 10 to the 23rd atoms. Okay, and we use this in our conversion factors. We always say that 1 mole equals 6.022 times 10 to the 23rd. We also remember saying that 1 mole will always equal the molar mass. And remember, the molar mass of an element is the atomic number in the periodic table. And then the molar mass of a compound is going to be the sum of all the atomic numbers in the compound. We're looking here at our conversion factors. When we go from grams to moles, we always want to use the molar mass. Remember, that's found on the periodic table, and if it's a compound, then it's the sum of all the atomic masses in the compound. And then whenever we go from moles to atoms, we're always going to use Avogadro's numbers, 6.02 times 10 to the 23rd. Okay, and some examples of these going back and forth. Here we see we're starting with 14 grams of carbon, and we want to go to moles. And since we have grams, going from grams to moles, we need the molar mass. So I know that 1 mole of carbon is going to equal the molar mass on the periodic table, which is 12.0 grams of carbon. So we can set this up just like always. We have 14 grams of carbon, and since grams is on top, we'll put grams on the bottom again, so it's just going to be 12.01 grams of carbon. Grams and grams match up, and those will go away. And then we put the other side on top, which is 1 mole of carbon. So when we work this out, we'll multiply the top, so 14 times 1 will give us 14 all over 12.01, which will give us an answer of 1.17 sorry, not times, but 1.17 moles. Okay, and all we do is we divide that out. So we have 1.17 here for moles. And we want to go from moles into atoms, so all we have to do is we have 1.17 moles, and that's of carbon, and we know that 1 mole is always going to equal of anything is going to equal 6.022 times 10 to the 23rd atoms. So all we do is we set this up. We can go easily to atoms. Since mole is right here, we'll put mole on the bottom. So we put 1 mole of carbon on the bottom, and we put 6.022 times 10 to the 23rd, and that's atoms. And since it's on the numerator and the denominator, they cancel each other out. We go ahead and multiply this guy out, and we would get 7.04 times 10 to the 23rd, and that would be atoms of carbon. Okay, kind of jumbling on that, but hopefully we can see the work that we did. All right, moving on to our second example. It says how many moles are in 109 grams of sodium chloride. So in the previous problem, we were dealing just with an element, so the molar mass was simple. We looked on the periodic table, but here we're dealing with sodium chloride, which is NaCl. So I need to know the formula of it, and I got that from its name. I just crisscrossed sodium and chlorine with their oxidation numbers, and I got the formula. And what I do with the formula is I figure out, well, how much of each do I have? So I have sodium and I have chlorine. I have 1 sodium, 1 chlorine, and I multiply those guys by their atomic masses. So sodium is 22.99, and we have chlorine, which is 35.45. We multiply those guys out and add them up, and we see we'll have 22.99 and 35.45. Add them up, and we'll have 58.44. Remember, that's grams in 1 mole. So I know that 1 mole of NaCl, sodium chloride, equals 58.44 grams of NaCl. So now that I have my conversion factor, I can set it up. I have 105 grams of NaCl, and I set it up. Since grams is on top, I put grams on bottom, which will be 58.44 grams of NaCl. We see that those cancel because of the same unit. We'll have mole on top. Multiply it out. It will be 105 divided by 58.44. And we see we get an answer of 1.80, and that would be moles of NaCl. Now moving on to wave calculations. Now wavelength is the distance between 2 peaks, and it's measured in meters. Frequency is the number of peaks that pass a point each second. We measure that in hertz. And we see that we have the equation for the speed of light, where we have wavelength times frequency, which gives us the speed of light. And we know that the speed of light is going to be 3.0 times 10 to the 8th meters per second. Looking at wavelength and frequency, we always have to mention the hydrogen emission spectrum. And we know that the hydrogen emission spectrum happens because what we have the ground states of those electrons. And when those electrons absorb energy, they become excited and they shift up to a higher energy level. And when those electrons drop back down, what they do is that absorbed energy is going to be released, and it's going to be released as light. And what we see is that each element has a very specific pattern and a very specific bright line spectrum. So we see that the hydrogen emission spectrum comes by having those bright lines that we can pick out from the spectrum, and we can label it to a specific element. Now, we're looking at frequency and wavelength. What we can see is here we have a very, very small portion of the electromagnetic spectrum, which is this entire thing right here, that is actually visible light. And we see that invisible light we have down here. And one thing we can notice from the chart is that over here we have low frequency, but it's a very high wavelength. And over here we have high frequency and shorter wavelength. So if we're to ask ourselves and looking at these wavelengths, well, the shorter the wavelength, we see the higher the frequency. So we're going to see that the purples are going to have the very highest frequencies, and the reds are going to have the very lowest frequencies, okay? Because the purples have very low wavelengths, and the red has very high wavelengths. Now, talking about the nucleus, and we have the discovery of the nucleus, and talking about it, what we see is that the nucleus contains the protons and the neutrons. And it's very small, packed, very tightly dense space. And we see that surrounding it, which we can see the nucleus is right here, and surrounding it in that yellowish hue is our electron cloud. And now our electron cloud contains our electrons. It contains in this area. Remember, we can't specifically point to where the electron is, but we say that it's in an area, and that area is going to be our electron cloud. And it takes up really the most space in the atom. The nucleus is very small and tight, but the electron cloud is very large. Now, we're talking about the s orbital, and the shape of it, obviously we see it in the center circle, so it's going to have a spherical shape. And then we have the 3p orbitals, and what we see is they combine in a dumbbell shape for us. So again, we have the S, which is spherical, and then we have the P, which is the dumbbell shape. When we're looking at those S, P, D, and S, we see that in the S block, which are over here, there are groups 1 and group 2. We see that they can only take 2 electrons, and that's why they only have 2 groups of them. Now, in the D block, which is the middle of the periodic table, made up of all elements, or all metals, so we have all our transition metals right here. The D block can hold 10 electrons, and we know that it can hold 10 electrons because it has 10 groups, meaning we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it has 10 blocks in it. We know that the P block, or the P sublevel, that it's going to have the ability to hold 6 electrons because obviously it has 6 groups in it, and then F can hold 14 because it has 14 groups in it. Now, the rules for arranging electron configurations, we have the Aufbau principle says that an electron occupies the lowest energy orbital that can receive it. So we know that it's going to fill at the very bottom, and we're going to go up to the top. Beginning in the third energy level, the sublevels get kind of mixed up. So we have to follow this order of filling, which we could see in the previous, how we fill the sublevels, and as we go through it, we count it with our blocks. Okay, so we have to follow that rule because it'll fill the lowest energy level possible. Now, the exclusion principle says that no 2 electrons in the same atom can occupy the same place at the same time. The Hund rule says that orbitals of a sublevel are each occupied by 1 electron before an orbital is occupied by a second. If we need help with electron configuration, guys, this is the link to the video that you need to watch. The video's on YouTube. It's the electron configuration part 1. And if you go ahead and take this right here, and if you need extra help on your electron configurations, just download this PowerPoint and go ahead and copy and paste this into your toolbar or into the address bar, and it'll take you to the video for electron configurations. Now, moving on to Mendeleev. Mendeleev was very important to chemistry because he was the first person to publish a periodic table. He recognized that elements had similar properties, so therefore he arranged them in his periodic table. Now, what Moseley did, Moseley was accredited with making our modern periodic table, our current periodic table, and he did this by arranging by the number of protons. So we arrange everything on the periodic table because of Moseley, and we arrange it by order of protons on the periodic table. Now we see that on the periodic table we have some special groups, and we see that group 18 is a very special group. It is called the noble gases. And one thing we need to know about the noble gases is that they are very, very stable, meaning they do not like to react with anything else. They already have their octet, their 8 electrons, so they don't want to mess with anybody. They're very stable, and they're very, very unreactive. Now, if you need help by looking at the other groups on the periodic table, you can check out the video, Periodic Families iPod Lab, and this is the link for that. Just click on that, and that will give you a lot more detailed information about the groups or the families on the periodic table. Now, in looking at the periodic table, it does give us a lot of information. One thing it does is we can see trends on it, specifically ionization energy. We see that ionization energy increases across a period and decreases down a column. So basically what we see is ionization energy increases as we get closer to up to helium. And what we see is ionization energy is how much energy it takes to create that ion to give it an electron. And we see that electron affinity is the energy change when an electron is added to the gaseous neutral. So over here, ionization energy, we're making an ion, we're taking that ion away, or taking that electron away, and then we see that electron affinity is when we add an electron to it. Okay, so the other one we're taking it away, electron affinity we're adding to it, but either way they have the same trend. They increase to the same way they increase to helium. Now, electronegativity we talk a lot about in the previous chapters, and we talk a lot about now. Remember, the electronegativity is a measure of how strongly an atom attracts electrons when it's in a compound. Main thing is when it's in a compound, they are not alone at all. They are bonded to something. And fluorine has the highest electronegativity, and it has an overall electronegativity of 4.0. And we see that it increases up to fluorine as well, so everything's getting higher to fluorine. So we see that ionization energy when we take that electron away, electron affinity when we add that electron, and electronegativity all increase toward the same direction. Remember, electronegativity is how much an atom pulls when it's bonded. And then we see atomic radius, it decreases in the exact opposite way. And we see it decreases to as we get closer to the bottom. And we see that atomic radius is just how it sounds. It is just the how large an atom is. And they measure that by going from a central of the nucleus to another a half of the difference between two bonded atoms that are together. Now, specific ions that we have cations and anions, and cations have a positive ion. It's caused by an atom losing an electron, and these guys, main things with cations that they are metals, and we see that anions are negative. Okay, so cations have a T, that they are positive. Anions have an N, they are negative, and they're negative because they gained an electron. Cations are positive because they lost an electron. It's a good thing to give things away. It's a bad thing to just be a taker and always take. Okay, so positive, it's good to give away. Negative, it's bad to take. So positive, negative, that's what we need to know about ions. Now, when we get into review now, we talk about naming compounds. If we have any questions on naming, we need to refer to the naming compounds practice problem, and this is the link for that you can go on and watch a video about naming. Same thing with formula mass. We see that formula mass, if you have any question with that, that's how we add up everything. You need to watch the second half of this video. The first half is the average atomic mass, and you don't need that for your test. You just need the gram formula mass, and you'll see that in this link below. Now, in dealing with chemical bonds, we say that the atoms, that they don't want to exist alone. The whole reason why something will bond is because they want to become more stable. They want to have less potential energy. So what a chemical bond is a mutual electrical attraction between the nuclei and the valence electrons of different atoms that bind the atoms together. Okay, a chemical bond is when two atoms are bonded together because of those valence electrons. And we see that we have two specific bonds that we talked about. We talked about ionic and covalent. Now, the main thing and the main difference between ionic and covalent, ionic, we see that we have the transferring of electrons. Covalent, we have the sharing of electrons. Remember, covalent needs the 8, it needs the octet. And with ionic, we're just transferring those electrons on down. The main thing, one of the main things we need to know is that ionic is between a metal and a non-metal. And we see that covalent is between a non-metal and a non-metal. Okay, so ionic, metal, non-metal, covalent, non-metal, non-metal. And we see we have the transferring of electrons in ionic, and we have the sharing of electrons in covalent. Okay, and another way that we can tell if something's ionic or covalent, or we see that covalent is broken up into polar covalent and non-polar covalent. Specifically, polar covalent, we're dealing with anything that has 0.3 to 1.7 difference in electronegativity. So we basically take the electronegativities of both of them and subtract them and get the difference. And if it falls within that region, it's polar covalent. Non-polar covalent is from 0 to 0.3. Main thing here, guys, non-polar covalent is always bonded to itself. Okay, non-polar covalent, if you see something bonded to itself, you know it's non-polar covalent. If not, we got to check out and look at the math. Into the octet rule, and we see that what an octet rule is it represents all elements sharing 8 valence electrons, and we see that a compound tends to form that each atom has 8 or an octet of electrons in its highest energy level by gaining, losing, or sharing electrons. So we see that everything needs 8, everything needs to have 8. So when we're looking at those Lewis structures, remember that we always look around and see if those covalent compounds have 8 valence electrons, because they need to have 8 valence electrons, because 8 is the magic number. Okay, and then we see, for exceptions to that, we see that the duet rule, which applies to hydrogen, helium, and those guys only need 2. But everything else needs 8 because they have to have 8 to be happy. Now, when we're looking at Lewis structures, and we need to know what goes in the middle of a Lewis structure, remember that carbon always goes in the middle of a Lewis structure. Hydrogen will never go in the middle of the Lewis structure. And the least electronegative, meaning the one that's farthest away from fluorine, if we don't have hydrogen or we don't have carbon, which we can put on the outside, then we always go with the least electronegative to put in the middle. Now, if we have any questions on Lewis structures, guys, there's a good video here for Lewis structures. It's on YouTube. Just paste that in there and go ahead and look at a YouTube video on the Lewis structures practice problems. Guys, looking at ionic characteristics, the higher the difference in electronegativity, the more ionic something is. The lower the difference in electronegativity, the least ionic it is. And that goes back to our chart, remember, of ionic, polar covalent, and non-polar covalent. Guys, percent composition we just went over. So we should have an idea. If we don't, there's a video for it for percent comp. It's on this link right here. Just go watch it. You'll learn all about percent composition. Same thing for empirical and molecular formulas. You can go on here. It's just the video that has empirical formulas and molecular formulas, and this is the link for it. Guys, if you have any other questions, make sure you come in and ask me before your final. Make sure we study hard. Remember, it's 20% of your grade. Good